Okay, so VSEPR theory stands for valence shell electron pair repulsion. And essentially what we're doing is all of these things are repelling each other. They want to get as much space as possible, so they try to maximize the bond angles away from each other. All right, and you'll see what I'm talking about here in a few minutes. So to predict these VSEPR structures, what we're going to do, we have to draw the correct Lewis structures. Okay, and you guys have gotten pretty good at that, so I'm pretty confident in that. We're going to put the pairs as far apart as possible, determine the positions of the atoms from the way the electron pairs are shared, determine the name, shape, and bond angles from that position of the atom. And as we come up with our chart, we're going to be able to see exactly which one happens from the Lewis structure. Now, we're specifically looking at how many things are attached to the center atom and how many lone pairs there are, not how many bonds it makes. So what you have to understand is a double bond or a triple bond to something still only counts as one thing attached. We don't count the number of bonds, we count how many things are attached. Okay? All right, so the first example we're going to look at is H2. All right, so we have to draw the Lewis structure first. Well, I have two H's. They're just going to bond together. Each one has how many valence electrons? Each one has one, right. So easy enough, when I draw my one in, I just bond them. Okay, there's no center atom when you only have two things. All right, so if you only have two things, this is automatically going to be called linear. And the cool part about linear that I know is that a line has how many degrees? How many degrees in a straight line? 180. So 180 degrees in a straight line, so that's my bond angle. And my VSEPR structure, okay, is going to look exactly the same. My VSEPR structure is going to look like that. Okay, so bond angle is 180 degrees. Here's what it looks like molecularly. Okay, just two things bonded together. Okay, our second one, CO2. Well, Lewis structure-wise, first off, C gets how many? How many valence electrons for C? 4. Each O gets how many? 6. So that's 12. My total is 16. What's in the middle? The C. Okay, so the C's in the middle with the two O's on the outside. C gets 4. Each O gets 6. All right, so connect, connect. Now, when I count, right now I have 7, 6, and 7. So what should I do? I'm going to make a double bond on either side right now. Okay, so I'm going to take the one from the top of the left-hand O and the one from the top of the C, and I'm going to make a double bond there. Okay, and I know it's a little bit sloppy, but just bear with it. Okay, so now at this point, this has 8 and this has 7. So what do I do now? Yeah, I'm going to take that single one from the bottom of the C there and the one from the top of the other O and make another double bond. All right, so at that point, everything has 8. All I have to do is count my total to make sure it's 16. All right, so 2, 4, 6, 8, 10, 12, 14, 16. Okay, so I'm good. Now, what I'm looking at is the center atom. Remember, this is my Lewis structure. Sorry. This is my Lewis structure here. And what I'm looking at is the center atom right here. What I need to look at is how many things are attached to it. How many atoms are attached to it right now? No. 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 Not 4, not 8, not 6. There's 2 things attached. There's one O attached here and one O attached here.
We're going to flip a breaker off.
So, I have an O attached on one side and O attached on the other. That's what I'm looking at. How many things are attached to it, not how many bonds are made. Okay? So, I have 2 bonded atoms. How many lone pairs on the center atom? No. Remember, this is a lone pair. That's what a lone pair looks like. There's none. Right. 0 lone pairs. Okay. When I have 2 bonded atoms and 0 lone pairs, this is also linear. Okay? But it's a little, it's a little bit different, but it's the same thing. And we just said linear has what bond angles? 180 degrees. Okay? When I draw the VSEPR structure, again, it's going to look exactly the same, except for I don't show any of the other stuff. I just draw it like that. Okay, that's my VSEPR structure for linear with two things attached. Okay, so the picture of this is going to look as such. Still, you see 180 degrees there. Okay, from, I don't know if I can draw on this, we'll see. From there to there, 180 degrees. Okay, all right, next one. ALBR3. Okay, so what's in the middle in the Lewis structure? Yeah, the AL. We said again, if you have one of something and multiples of something else, if it's not carbon there, the one is going to be in the middle. So I'm going to draw AL with the 3 BRs on the outside. Okay, AL gets how many? 3. All right, so I know right away this is going to be an incomplete octet. BR gets 7 each, so that's 21, a total of 24. So easy enough. It's going to bond there, fill in my dots. Bond there, fill in my dots, and bond there and fill in my dots. I'm assuming by now you can draw this Lewis structure without a problem. All right, so to go to the VSEPR structure, I look at the center atom. Again, how many things attached? 3. 3 bonded atoms. How many lone pairs on the center atom? 0. Okay, so the name of this, if you have 3 bonded atoms, 0 lone pairs, is trigonal planar. What that name means is this, and when I do the drawing, you'll see exactly what I'm talking about. Trigonal means triangle. Planar means it's flat. It's not 3D. It's in one plane. Okay. So let's draw what this looks like. Now, first off, I have the AL in the middle. Okay, so this is going to be my VSEPR structure again. And basically, it looks like a Y shape. So the BR is going to be one up here, one down to the left, one down to the right. Now, knowing that a circle's 360 degrees, what would I expect the bond angle to be then between each of the BRs? What I'm asking is, what do I expect the bond angle to be from here to here, basically? If a circle's 360 degrees.
120.
120, good. So my bond angles here are 120 degrees, every one of them. All right, trigonal planar, 120 degree bond angles. Here's what it looks like. Okay, and again, you can see from there to there, 120 degrees. The whole circle, remember, is 360 degrees. 120, 120, 120 gives me 360. All right, next one here. SiCl4. All right, Lewis structure, what's in the middle? The Si. Okay, with 4. The CLs are on the outside with 7 each. I draw that small so it fits there. Okay, I'm on that. All right, so center atom is the Si. How many bonded atoms? And I'm going to abbreviate this BA. 4 bonded atoms. How many lone pairs? 0. Okay, 4 bonded atoms, 0 lone pairs. This is called tetrahedral. Okay, we know tetra means 4 from doing our naming for covalent compounds. Now, this is where the drawings get a little bit more interesting because we start using wedges and dashes to represent what's coming towards us and what's going away from us because now we're in 3D. All right, so here's how we draw this. And pay attention because this is going to be kind of useful as we move on to the bigger ones too. So Si is in the middle. I draw 1 up to the top. I draw 1 down either to the left or right. I like to do it to the right just by convention. To there. Then, no matter which way I turn it, I'm always going to have 1 pointing at me. So the one that's pointing at me goes down and is wedge-shaped. That represents that it's coming out towards me. The one that's in the back, because there's always going to be one in the back, is a dashed line like that. Okay, and you should be able to see kind of the 3D nature of that. It looks like a tripod. Okay, so you have to get used to being able to draw these. The bond angle for tetrahedral, okay, and this is going to be a little bit weird, is 109.5 degrees. All right, 109.5 degrees, and here's what it looks like in space. Okay, one coming towards us, one to the side, one going away from us.